Now I'm going to discuss utility measurement. In expected utility, the utility function completely describes the risk attitude of a person. If you know the utility function of the person, you know in all risky situations what the person will do. So therefore, it's important to be able to measure the utility function. For instance, you can imagine if you're an insurance company, you're thinking whether to settle in Amsterdam or Rotterdam, then you want to know where people pay the highest premium for the risk that they take. And we're assuming expect utility now, then it means you should measure the utility function of the people in Amsterdam, of the people in Rotterdam. Then you know what premiums they pay for the risk that they have, and then you can see where they pay the highest premium, so you can make most money. That's where you settle down. So that would be one simple example. But now in general, we're going to consider the question, how measure utility. For instance, how can you measure the utility of 30 euro of a particular person? And I'm going to assume, as we did before, that the utility of 0 is 0 and the utility of 100 is 1. That's a normalization that I assume later you will see we can always do it. Now you just give me that one. Now we're going to assume also that you are in the experimental heaven, and it is an as-if model. So if you say, oh, I go to the person, ask him, what's your utility of 30? He will say, a utility I never heard of, I don't know what it is. So we have to do the economic reveal preference game. We will observe choices and preference from that person and derive from that what the utility of 30 is of that person in this as-if model. We will assume, as in the first meeting, that you are in the experimental heaven. You can ask any preference question to the person and the person will answer. Any choice situation, you can find out what the person does there. No measurement error, you get perfect measurement. So with that understood, I ask you in a moment to pause the video and think for yourself. Can you think what kind of question, what kind of choice question would you ask the person to find out what the utility of 30 is? Okay, now you can pause the video, think for a while. Okay, I assume you came back, you thought about it as long as you want. Then now I show you one of the ways common way to measure utility under expected utility. We start with, well, here's a lottery giving you 100 or 0 with a probability yet to be determined. And you ask the person, imagine you can choose either 30 for sure or this lottery with probability. Now, which probability here makes it too indifferent to you? The person thinks for a while, then comes the answer. The person says, P is 0.4. So if P is bigger, the person prefers the lottery. If P is smaller, the person prefers a sure amount. P is 0.4, person is indifferent. You already see that this person is not doing expected value maximization. Then P is 0.3 would be the equivalent, the certainty equivalent. Now you can pause the video again and do some calculation to see what the utility of 30 is in this situation. Okay, I now show you, I continue now, I now show you what that is. So we do the calculation. In the calculation, because these two are indifferent, the expected utility of 30 for sure must be the same as the expected utility of that lottery here. So we calculate the expected utility, we get the equality, and that gives us what we want. Here is the calculation. The expected utility of 30, of course you get it with probability 1, is just utility of 30. The expected utility of this lottery, and I'm assuming P.4 now, is 0.4 times utility of 100, that's 1, so that's this term. 0.6 times utility of 0, that term. 0.4 comes out of it, and then you see utility of 30 is 0.4. So this was a very easy, about the easiest way to measure utility under expected utility. You can do more measurements of this kind because you want to know more, you want to know the whole utility function maybe. Let's say you do it also for 70. You want to find out the utility of 70, and it's the same pattern that you use. You present the person with a lottery giving you 100 or 0 with a probability Q to be determined. You ask the person which probability Q makes this lottery equally good to you as getting 70 for sure. Imagine the person says Q is 0.8. And then the same kind of calculation as before, I think you immediately see it. The utility of 70 must be 0.8 in this situation. Now, if you have enough measurements of this kind, you can measure the graph of the utility function to the desired degree of precision. For instance, I draw the graph now. So money on the x-axis, utility on the y-axis. 100 and 0 we already know. At 0, we say that the utility is 0. At 100, we say the utility is 1. You give me that one for now, it can be done. Then we have for 30, the utility is 0.4. For 70, the utility is 0.8. And already you get an indication of what the graph of the utility function can be. So this is in principle how you can measure utility functions of persons. In general, let me repeat this thing in general formulas. In general, this method is called the standard Campbell method. The situation is you have some range of outcomes of your interest, the best outcome capital M, the worst outcome small m. We can always normalize utility and have utility capital M1, utility small m0 if we want. You believe that for now. Then we take for any outcome alpha between the two m's, you ask the person, in this lottery, which probability P makes the lottery equally good to you as alpha? And then by calculation, and you can do it, you see utility of alpha must be expected utility is P times utility of M is 1 plus 1 minus P times 0, that's P of course. This measurement gives you immediately utility of alpha as P. For instance, this is also used, I gave you the example of insurance company in many applications. In the health domain, for instance, people often use the term quality of life, which is about the same as utility. And for instance, the way how it goes, often in the health domain, the best conceivable outcome is perfect health. The worst conceivable outcome is death. So then we set utility 1 and 0 at those extremes. That's the common normalization in the medical domain. Then if we want to find out the quality of life of being blind, we find out for a person what is equally good, being blind or having a lottery, maybe a risky operation that can give back perfect vision, perfect health, but has a mortality rate, say 4% of people die from the operation. And then, so you find out, and let us say you found out that with probability 0.96, this person is willing to take 4% probability of dying for the possibility of getting perfect vision. And of course, you can't do it just like that. You need a good psychologist and explain to people how things are. But this is done in very careful manners in the health domain. And this is a common measurement. If you find this result, then you say the quality of life of blindness is 0.96. That means if you get blind, you lose 4% of the quality of life. And such measurements are used to decide on medical treatments, how much money to spend on treatments, because we want to make the biggest gain of quality of life. Quality of life corrected life years is often used quantity. Anyway, these measurements are often used in the health domain for making decisions there. Now, in the next section, mostly in the next recording, will be on consistency of measurement. But already now I present a preparatory notation for that next section, for 2.6. That is multi-stage lotteries. Imagine chance node 0.5 going up, 0.5 going down, but you don't get a money amount immediately. There's another risk to be resolved in the upper branch. You end up in another circle, chance node, and again probability distribution. It may go up or down, probability 1/3, 2/3, outcomes 200, 0. Lower branch the same, second stage probability 1/3, 2/3, giving you 100 or 0. So here the uncertainty is not resolved in one stage, but there are several stages of resolution of risks. And in many applications, it's not one stage, but it's a very complex multi-stage models that you have. So this often happens. So we do a rule for evaluating is that probabilities are multiplied. For instance, we say this is equal to, let us see, it can give you outcome 200, which probability half times 1/3 is 1/6. So 1/6 probability of getting 200. It's also possible that you get 100. Probability is half times 1/3, again 1/6. And there's also 0 is possible. There's a half times 2/3 is 1/3 probability coming from here. Also 1/3 probability coming from here. In total, 2/3 probability of 0. This is how multi-stage lotteries are evaluated using the rule of probability multiplication. And with that understood, I go to the next section, but that will be the next recording.